Hi everyone, welcome back to the channel, and it is a continuation of classes on the topic coordination chemistry. And in this video we shall try to learn about the concept of ligand, its core meaning, the detailed classification of ligands, and shall give the exemplifications for each and every type of the ligand, and we shall focus on how to pronounce the ligands depending upon whether it is a neutral one or whether it is charged one. All those things we shall learn in this particular video. So first we shall see the exact meaning of ligands just by giving the definition of it. A ligand means, we said in our previous video, that in a complex ion or in a coordination sphere, the central metal ion will be surrounded by certain definite number of ions or molecules which formed coordinate bonds with the central metal ion. In order to form the coordinate bond with the central metal ion, the ions or molecules are supposed to donate the electron pairs to the central metal ion. For one electron pair donating by the ions or molecules, there develops one coordinate bond between the ion or molecule and the central metal ion. So such ions or molecules which are having capability to donate one or more pairs of electrons to the central metal ion and thereby developing the coordinate bonds with the central metal ion, such ions or species was simply considered as ligands. So that is the simplest meaning of ligands. And just now we said a ligand can be ion, that may be a positively charged or negatively charged, and a ligand can be a molecule also. And the ions are also molecular ions. Either an atom is present or more than one atom may be present in ions also. And in that case, if more than one atom is present in an ion or molecule, it is not possible to say that all the atoms of molecule are having capability to donate the electron pairs to the central metal ion. Any one particular atom will be having that capability so as to donate the electron pairs to the central metal ion and thereby developing a coordinate bond. So in the ligands, the atom of the ion or molecule, or in a strictly speaking way, the atom of the ligand, that can be an ion or molecule, the atom of the ligand which is donating the electron pairs to the central metal ion will be called as donor atom, or it can also be called as coordinate atom. But in general, we used to call that atom as ligating atom. Ligating atom. This is the word we regularly use for the atom of the ligand which donates the electron pairs to the central metal ion. So depending upon the number of electron pairs donating by a ligand to the central metal ion in forming a coordinate bond, that is, depending upon the number of ligating atoms present in a ligand, ligands can be easily classified. And now we shall see the detailed classification of the ligands based on the number of ligating atoms present in it. So under classification of ligands, we said the classification of ligands will be made based upon the number of ligating atoms present in the ligand. So on that basis, the very first type that comes under ligands is unidentate. So uni in the sense one, so we can also call this as monodentate ligands. Unidentate or monodentate ligands. So the name itself telling you the ligand of this type will be consisting of only one ligating atom. And we said each ligating atom will be having capability to donate one electron pair to the central metal atom or ion. So the ligands of this type, that is monodentate ligand, will be having one ligating atom. The monodentate ligands will be having one ligating atom, and since there is only one ligating atom, they can donate or they can form only one coordinate bond with the central metal atom or central metal ion by donating one electron pair to the central metal ion. So that's about the simple way of understanding the term unidentate or monodentate ligand. They will be having only one ligating atom, and thus they can form only one coordinate bond with the central metal ion or atom just by donating one electron pair to the central metal ion. And as I said, a ligand can be a neutral one, can be a charged one. Charged in the sense it can have a positive charge or it can have a negative charge depending upon the ligand. So under monodentate ligand, we are having more number of neutral ligands, negatively charged ligands, as well as the positively charged ligands also. And now we shall see how we are, which are those ligands that comes under monodentate ligand and how we are supposed to pronounce all those ligands. So firstly, we shall go with neutral monodentate ligands. So in that, the very first one is CO, that is carbon monoxide, and this is supposed to be pronounced as carbonyl. We should pronounce the carbon monoxide ligand as carbonyl. And secondly, NH3. So here the ligating atom is nitrogen, because on nitrogen there will be presence of the lone pair of electron which can be donated to the central metal ion. And this is ammonia. But when ammonia is acting as ligand, we are supposed to call it as amine. So hope you can observe how I have written the spell for the amine, A-M-M-I-N-E. Okay, so that is the way we are supposed to write the name for the ligand, NH3. And the next ligand is H2O. Here the ligating atom is oxygen. So though there are two lone pair of electrons on the oxygen atom, only one electron pair will be donated to the central metal ion. So this also comes under monodentate ligand only. When water is acting as ligand, this is supposed to be pronounced as aqua. Okay, and NO. So we know this is nitric oxide, and no charge is present on this. So when NO, when it is acting as a ligand, it's supposed to be pronounced as nitrosyl. And PH3. So at the place of nitrogen we are having phosphorus. So like in nitrogen, on phosphorus also there will be one lone pair of electron that will be donated to the central metal ion, and this will be called as phosphine. Okay, and then after PH3, so here in PH3 we are having three replaceable hydrogens. When all these three hydrogens were replaced with the phenyl groups, so we can write the thing like this. So phenyl group C6H5, all the three hydrogens have been replaced with the phenyl groups and phosphorus. So it is phosphine, and it is the derivative of phosphine wherein the hydrogen atoms were replaced with phenyl groups, and there are three phenyl groups, and it is obtained from phosphine. So it is triphenyl phosphine. That is the name of this ligand. And nextly, the heterocyclic compounds also acts as ligands. So this is pyridine. So pyridine also acts as ligand. So pyridine. So whenever pyridine is acting as ligand, instead of writing the full name, so it will be mentioned as just PY. So whenever you are having py symbol in the formula of a coordination compound, that is understood, the ligand is pyridine, wherein the ligating atom is nitrogen atom of the heterocyclic ring. So these are some simple examples for neutral monodentate ligands. And now we shall go with the negatively charged monodentate ligands. So the first one, let us go with the halogens, that is F minus. So it will be called as fluoro. So just like halo. And remember, whenever you are writing the name of a negatively charged ligand, the name of that negatively charged ligand should end up with the letter O. That should be remembered. The name of the negatively charged ligand is supposed to be ended up with the letter O. So fluoro, F minus, it is calling us fluoro. And if it is Cl minus, so we should call it as chloro. And if it is Br minus, then it is bromo. Then it is I minus, we should call it as iodo, like this. So if the ligand is Cn minus, so in the first four cases there is only atoms, F minus, Cl minus, Br minus, I minus, these all are atoms. But here we got the molecules, both carbon and nitrogen. So in this case, both carbon and nitrogen, any one can act as a ligand. Depending upon the atom of this particular group which is acting as ligating atom, the name of the ligand will get changed. So for example, so when the ligating atom is carbon atom, then it will be called as cyano. But instead, when the ligating atom is nitrogen, then it will be called as isocyano. As I told, the name should end up with the letter O. Then H minus. So we know that the name of this particular symbol, that is H minus, we call this as hydride. Whenever hydrogen is existing in the oxidation state of -1, we used to call it as hydride. The last letter E is supposed to replace with the letter O. So the name will get changed into hydride. That will get changes into hydrido. Then CH3COO minus. And here the ligating atom is the last oxygen. And we know that CH3COO minus is acetate. The last letter will be changed with the O. So it will become acetato. That is the way we change the names of this negatively charged ligands. And now we shall continue with a few more negatively charged ligands. OH minus. So this is hydroxide, right? So this will be called as hydroxo. And if it is NO3 minus, so we used to say this as nitrate. So the last letter will be replaced, nitrato. Right. And if it is SCN minus, so here also we are having three atoms. So S, C and N. But among these three atoms, either sulfur or nitrogen can act as a ligating atom. If sulfur of this particular group is acting as a ligating atom, then it will be called as thiocyanate. This is thiocyanate actually. The last letter E should replace with the letter O. So it will become thiocyaneto. But after writing this name, that is thiocyaneto, we should indicate among the sulfur and nitrogen which is the ligating atom. So here the sulfur is ligating atom. So thiocyaneto S. And instead of sulfur, if nitrogen is acting as ligating atom, then again the same thiocyaneto itself the name, but the ligating atom is N. Okay, so like this we should replace the names by indicating the ligating atoms. And we shall say two more things. Say for example NO2 minus. So it is nitrate, right? So NO2 minus is nitrate, and here also either nitrogen or oxygen can behave as ligating atom. So depending upon which atom of this particular group is acting as ligating atom, the names of those ligands will get changed. So for example, here if we have written the molecular formulae like NO2 minus, then that indicates the ligating atom is nitrogen. Then we should call it as nitrito, and the ligating atom is N. Whenever the oxygen atom of this particular group is acting as ligating atom, then we write in this way ONO minus, and here the ligating atom is oxygen. Then the name will be nitrito itself, but we should indicate the ligating atom, that is O. So these are some of the examples for the negatively charged monodentate ligands. And let me give you some simple examples for positively charged monodentate ligand. So if you have considered nitric oxide, NO. So in previous case, that is in case of neutral monodentate ligand, we said nitric oxide is neutral. In that case, we used to call that as nitrosyl. But whenever this NO group is carrying a positive charge, and when that acting as a ligand, we call that NO plus as nitrosonium. And we said the name of the negatively charged ligands are supposed to end up with the letter O. And the names of positively charged ligands is supposed to end up with the suffix IUM. Okay. And so that the name of the ligand NO plus is nitrosonium. Suppose if it is NO2 plus, then it is called nitronium. Again, it is ending with the suffix IUM. So once again, one more, NH2, NH3, positive charge. We know that NH2, that is hydrogen. But by adding one more hydrogen, one of the nitrogen got the positive charge. So its name will get changes into hydrazinium, ending with the suffix IUM. And this is the whole and sole thing about the monodentate ligands and the detailed exemplifications and their names. And now the second type of ligands are bidentate ligands. So the name itself telling you bi, that means these kind of ligands will be having two ligating atoms. So due to presence of two ligating atoms, these ligands are having capability to donate two electron pairs to the central metal ion so as to form two coordinate bonds with the central metal atom or central metal ion. So that is the simplest way we can understand about the term bidentate ligands. There will be two ligating atom so that they can form two coordinate bonds with the central metal ion just by donating two electron pairs to the central metal ion. So now we shall look over into some simple examples of this bidentate ligand. And like monodentate ligand, in case of bidentate ligands also, we will be having both neutral as well as charged ligands. And now we shall go with the exemplifications and the names of the bidentate ligands. The very simple example for the bidentate ligand will be this one. So this is the one which is obtained from the oxalic acid. So the two hydrogens have been removed, and that's why these two oxygen atoms are having negative charge. So negative charge means one pair of electron, and that can be donated to the central metal ion. So totally we are having two ligating atoms over here, and once again it is a negatively charged, so it is negatively charged bidentate ligand. So it is oxalate ion, but as we said, the name of the negatively charged ligands is supposed to end up with the letter O. So oxalate, the last letter E will be replaced with the letter O, so that it will become oxalato. That is the name of this ligand. But in order to simplify, or for the convenience of writing the formula of coordination compound, whenever we are having this oxalate ion, instead of writing this complete formula, we may have in this way C2O4. This is the condensed way of writing oxalato ligand, or else we can write it as OX. OX is a symbol for oxalato ligand, or you can have C2O4. So once again I am telling, this is a negatively charged bidentate ligand. And one more example we can give, that is CH2 NH2, CH2 NH2, and here the ligating atoms are these two nitrogen atoms. These two nitrogen atoms will be carrying the lone pair of electrons, and those two lone pair of electrons can be donated to the central metal ion, so that this ligand can form two coordinate bonds with the central metal ion or atom. So hence this will be coming under bidentate ligands, and hope you can observe there is no charge present on this ligand, thus it comes under neutral ligand. And since there are two ligating atoms, so it is neutral bidentate ligand, and it is called ethylene, and we are having two amine groups, and observe the spell diamine. Here I have not used double M, only one M is present. Whenever you are having NH3 acting as ligand, then only you have to use the spelling, that is AMMINE, but here we are using only one letter, that is AMINE. Please make a note of it. So it is ethylene diamine. So simply it will be abbreviated as EN. So ethylene diamine, that is EN, is a neutral bidentate ligand. So one more example we can give. NOH, OH, CH3, CH3. So we can notice this particular bond. We used to call this as oxime link. So we are having totally two oxime links, and it is the derivative of the two carbon atoms. So totally 1, 2, 3, 4 carbon atoms are there, and these are the carbon atoms to which the oxime group is present, and this is called as dimethyl, and there are two oxime group, so it is called glyoxymeto or dimethyl glyoxime anion. So simply it is called dimethyl glyoximate, sorry, not oxymeto, oximate anion. Actually it is when these two hydrogen atoms were removed, we will be getting the two oxygen atoms as, or else we can directly write it as, okay. So it is dimethyl glyoximate is the ligand, and here also it coming under bidentate ligand, that is this nitrogen atom can act as ligating atom, but when these two hydrogen atoms were removed, we will be getting the negative charge. But in general, this particular complex, this particular group, when it is acting as ligand, the two nitrogen atoms itself will act as ligating atom, and since it is also not carrying any charge, so this also comes under the neutral only. So dimethyl glyoximate is once again a bidentate, strictly speaking a neutral bidentate ligand, and like the remaining two, this also can be expressed in a simple abbreviated form as DMG, methyl glyoximate. So we can give a few more examples for bidentate ligands. Say CH2, COO minus and NH2. So hope you can notice this is the complete formula. This is the anionic form of the amino acid glycine. And here this negative charge will act as one ligating atom and this nitrogen atom will act as one more ligating atom. So totally two ligating atoms are there, but since it is carrying a negative charge, so it comes under the negatively charged bidentate ligand. Since it is an anion, so we used to call it as so it is called as glycine or glycinate it is. So glycineto. Since it is the negatively charged one, the name is ending with the letter O. So it is glycineto. And simply it is abbreviated as gly. And one more, say C double bond O, CH double bond C, CH3, and here we will be having single bond with one negative charge, and here CH3. Here this oxygen atom and this negative charge, these two things will be having a lone pair of electrons on the oxygen atom, right? So one of the lone pair will be donated and this negative charge will be donated. So there are two ligating atoms here, and since having negative charge, this is also an anionic ligand, strictly speaking negatively charged bidentate ligand, and it is acetyl acetonate anion. So we used to call this as acetyl acetonato. That is the simplest name of this material. Okay, so it can be simply abbreviated as ACAC, acetyl acetonato. Okay, so this is also the anionic bidentate ligand. So one last example for bidentate ligand, that is, we said pyridine will act as a ligand, a heterocyclic compound. So whenever we are having bipyridine, this one, so like this can also act as a bidentate ligand, where we are having nitrogen atoms. The nitrogen atom will be having the lone pair of electrons on it, and that will be donated to the central metal atom. So here this is the position. So 1, 2, and again 1, 2 dash. So it is 2, 2 dash. The whole and sole compound is a dipyridyl. So dipyridyl. So this can be simply abbreviated as di-P. So for pyridine, just Py will be written, since we are having two pyridine units. So it is di-P, like this. So di-P is the abbreviated form for this bidentate ligands, and that's the meaning as well as the simple examples of bidentate ligands. The last type of ligands based on the number of ligating atoms is polydentate ligands. The name itself telling you polydentate, that means there will be more number of ligating atoms present in that particular ligand. And in particularly, a polydentate ligand means that will contain more than two ligating atoms in it. So if a ligating atom is having more than two ligating atoms, then that ligand will be having capability to donate more than one electron pairs to the central metal ion or central metal atom, so as to form more than two coordinate bond, more than two coordinate bonds with the central metal atom or central metal ion. Such kind of ligands are simply called as polydentate ligands. Say for example, if the number of ligating atoms are 3, then that will be called as tridentate ligand. And if the ligating atoms are 4, then it will be called as Tetradentate Ligand. So if it is 3, Tridentate. If the number of ligating atoms are 4, then it will be called Tetradentate Ligand. And if the number of ligands are 5 and number of ligating atoms are 6, the name will just go on changing. So if the number of ligating atoms are 6, then it will be called as Hexadentate Ligands. And if it is 5, then it is called Pentadentate Ligands. So all these tridentate, tetradentate, pentadentate, hexadentate and so on. So all these ligands will come under Polydentate Ligands, which consisting of more than 2 ligating atoms in them. So let me give one simple example for Hexadentate Ligand. So the Hexadentate Ligands is this one, CH2, CH2, N. So we know that when each nitrogen atom is attached with 2 hydrogen atoms, we used to call that as ethylene diamine. Suppose if the 2 hydrogen atoms present at each nitrogen atom, if it is replaced with an acetate ion, like this. So all the 4 hydrogen atoms have been replaced with acetate ion, and you can notice there are 4 negative charges and that is present on the oxygen atom. So these 4 oxygen atoms carrying the negative charge will act as ligating atoms, and anyway will be lone pair of electrons on the nitrogen atom. These lone pairs will also be donated to the central metal ion. So these 2 lone pairs and 1, 2, 3, 4 negative charges and 2 lone pairs present on the nitrogen atom. So totally 6 pairs of electrons are available on this particular ligand. Hence we can call this as Hexadentate Ligand. And since it is the derivative of ethylene diamine, by inserting 4 acetate anions, we used to call this as ethylene diamine. And since there are 4 acetate groups, so it is tetraacetate. Since it is the negatively charged, so the name should end with O. So tetraacetato. That is the way of writing the name for this particular hexadentate ligand, which is coming under Polydentate Ligand. So this can also be simply abbreviated as E, D, T and A. E, D, T, A. Ethylene diamine tetraacetato. In a strictly speaking, we can also mention the number of negative charges present on the ligand. So this is about the classification of ligands just based on the number of ligating atoms present on the ligand. So apart from all this, we are having 2 special cases under ligands that we shall see now. The special case number 1 is chelating ligands. So here, if you consider a coordination compound, in that if the ligands present are either bidentate or polydentate ligand, that means there will be having 2 or more than 2 ligating atoms which are surrounded by the central metal ion. In that case, the ligand is having capability to form more than one coordinate bond with the central metal ion. So for example, I am having a central metal ion and one bidentate ligand is present. Bidentate ligand means the ligand is having 2 ligating atoms so that it can form 2 coordinate bonds with the central metal ion. So by forming the 2 coordinate bonds with the central metal ion, this ligand is forming a ring structure with the central metal ion. And if a ligand is having capability to form a ring structure, with the central metal ion by forming more than 2 bonds, strictly speaking more than 2 coordinate bonds with the central metal ion, then such a ligand will be called as chelating ligands. And the ring structure which is formed between ligands and central metal ion due to formation of more than 2 coordinate bonds between ligand and central metal ion, that ring structure formed is simply called as, since the ring structure is formed by chelating ligand, that ring structure is called as chelate. So the ligands which are having capability to form ring structure with the central metal ion are called chelating ligands, and the resulting ring structure is called as chelate. And the chelates which are formed by the ligands possess greater stability compared to normal coordination compounds. So if you consider one simple example, say FeC2O4 thrice. So C2O4, that is oxalate ligand, so that will be having 2 negative charges on it. And let us consider here iron is existing in 3+ oxidation state, and there are 3 oxalate ligands are there. So 3 2s are totally 6 negative charges are there, and 6 negative charges, and there are 3 positive charges, so that on the complex there remains 3 negative charge. So this is the complex ion we are considering to explain the chelating ligands and the formation of chelate. So here, so Fe3+ will be present at the middle, since we have taken this as a central metal ion, and with this Fe3+, the oxalate, so C double bond O, O minus, C double bond O, O minus. So this will form 2 coordinate bonds, and one more like oxygen, C double bond O, one more carbon, oxygen double bond O. So here also 2 more coordinate bonds, and once again we'll be having CO double bond O, C double bond O, O. So this is 1 and 2. So here we got 1, 2, 3, 4, 5, 6. Totally 6 coordinate bonds were formed by 3 oxalate ligands, since it is a bidentate ligand. So here you can notice the formation of a ring structure with a total keeping 3 negative charges. Okay, so that this is the way of representing the chelating ligands and the formation of chelate. So this is the carbon atom. So this is the way we can represent the formation of chelate, and this is one simple example for the chelating ligands and chelate. So let me say once again, if a ligand by forming more than 2 coordinate bonds with the central metal ion, if it develops a ring structure with the central metal ion, then such ligands are called chelating ligands, and the resulting ring structure is called chelate. The next special type of ligands is ambidentate ligands. So these ambidentate ligands are very special because if you consider a monodentate ligand itself, in that monodentate ligand, see the meaning of monodentate is consisting of only one ligating atom, but in actual meaning, in case of ambidentate ligand, the ligand will be a molecule. There will be possibility of more than one atom can behave as a ligating atom in case of monodentate ligand. I repeat, in case of monodentate ligand, if the ligand is a molecule, whatever it may be a neutral or a charged one, there is some possibilities in certain ligands that more than one atom may show tendency to form the coordinate bond or to act as a ligating atom. But though more than one atom is having capability to act as a ligating atom, but ligation, that is donation of electron pairs to the central metal atom or ion, will occur through one atom only. Such monodentate ligand consisting of more than one, or in a strictly speaking way, two ligating atoms. Two atoms can act as ligating atom, but ligation takes place through only one atom. Such monodentate ligands are called ambidentate ligands. So we can give simple examples. Cn-, and here both carbon and nitrogen both are having tendency to act as a ligating atom, but when carbon is acting as ligating atom, nitrogen will remains normal. When nitrogen is acting as ligating atom, carbon remains normal. That means when carbon atom of this Cn- is acting as ligating atom, we call this as cyano. And when nitrogen atom of the group is acting as ligating atom, then we call this as isocyano. So the molecular formula remains the same, one carbon and one nitrogen, but the atom of the group acting as ligating atom is different. So that's why we are having two different names, cyano and isocyano. So we can give one more example for this, SCN, thiocyanate. Here both sulfur and nitrogen can act as ligating atom. If sulfur is acting as ligating atom, then we call this as thiocyanate, but the ligating atom is sulfur. When nitrogen is acting as ligating atom, the name will be given as thiocyanate only, but the ligating atom is N. One last example for ambidentate ligand, NO2 with one negative charge, and here also we'll be having the negative charges. So NO2-. So here both nitrogen and oxygen both are having capability to act as ligating atom. But when nitrogen is acting as ligating atom, oxygen remains normal. When oxygen is acting as ligating atom, nitrogen remains normal. So in this case, when nitrogen is acting as ligating atom, we call this as nitrito. And if oxygen is acting as ligating atom, then it is called once again nitrito only, but should mention the ligating atom O. And here nitrito, the ligating atom is N. So these are some simple examples for ambidentate ligand. So once again I am telling the meaning of ambidentate ligand, a monodentate ligand wherein more than one atom can act as ligating atom, but ligation occurs through only one atom. Such monodentate ligands are called ambidentate ligands, and these are some simple examples of ambidentate ligands. So that's all about the classification of ligands, and in the next video we shall try to learn about the concepts of coordination number, identification of charge on the complex ion, as well determination of oxidation state of the central metal ion present in a given coordination sphere. If you feel the video is worthy and useful, please like it, share it, and do subscribe to my channel. Press the bell icon so that you will get the notification for any update in my channel. Thank you.